All right, hello everyone. This is the 2023 spring final exam. Let's get straight into it. Number one, suppose ABC vector is a unit vector. Find an equation of the plane with normal vector ABC that contains the point ABC. Okay, so I think if we write out the equation of the plane, it's going to start to make sense. Just, of course, A times x minus A plus B times y minus B plus C times z minus c equals 0. That is just the standard form of a plane. And then we can, of course, distribute ax minus a squared plus by minus b squared plus cz minus c squared equals 0. And I think we're going to see something pretty cool happen here. If we add all the a squared, b squared, and c squared to the right side, we're going to get ax plus by plus cz equals a squared plus b squared plus c squared. And given like the definition of a normal vector, or sorry, unit vector, it says it's a unit vector, so this whole thing right here is going to be equal to 1. So, and hopefully that's our answer. Yeah, I saw C is our answer here. Number 2, identify the quadric surface 16x squared plus 4y squared minus z squared minus 64x plus 80. Okay, that's pretty long. Hopefully we can do it. Okay, I always like factoring out here. It just makes it easier to see. So I'm going to factor out the 16x and negative 64 here. So we're going to get 16 times x squared minus 4x. And of course, we're going to complete the square here, but we can do that later. And then, of course, plus 4y squared minus z squared. And then some plus 80. It's going to be equal to 0. I left a space here because when we complete the square, we're going to need to subtract something from the same side. So I'm going to add 4 here, of course, to complete the square. And that means we need to subtract 64 from the same side to make sure that you're not inappropriately manipulating the equation. And, of course, we can factor this out. We're going to get x minus 2 squared plus 4y squared minus z squared equals, I guess we can keep it like how it was, plus 24 equals 0. And, or this is not plus 24, this is plus 16 equals 0. And, of course, we can, I think it's going to make sense if we add together all the variables on the right side. So we're going to get 16 equals z squared. We're going to subtract x because it's positive, minus, 16x minus 2 squared minus 4y squared. And, of course, we can divide everything by 16, and we're going to get 1 equals z squared over 16 minus x minus 2 squared minus y squared over 4. And hopefully recognize that that is a hyperboloid of 2 sheets. And I think a quick trick is if there's 2 negatives here, it's 2 sheets. If there's only 1, so say it was just like plus x, that would be 1 sheet. So yeah, that is fine there. Number 3, a particle with initial velocity v of 0 equals 1, negative 1, 1 has acceleration a of t equals 4t, 61. Find the speed of the particle after time t equals 1. Okay, so give us acceleration. We can pretty easily integrate that to find velocity. So v vector of t is going to be equal to 2t squared. I'm going to leave a space here because we need to do some initial value stuff later. 3t squared, again, leave a space, t. So we want, when we plug 0 into t here, we want the vector to be 1, negative 1, 1. So, and since we just have t's right now, all we need to add is, we could just do plus v0, or in just our vector here, we could just do plus 1, minus 1, plus 1. Just makes it a little bit more shorthand here. So, and then now we just need to plug in v at t equals 1. So v at 1 equals, it's going to be 3. 3 minus 1 is 2. 1 plus 1 is 2. And, of course, looking for the actual speed. So we need the magnitude of v of t, which is just square root 9 plus 4 is 9 plus 8. And that is just root 17, and yeah, that is E here. Very nice. Number 4, a blue plane B is given by x plus 3y minus 3z equals 6, and a yellow plane is y given by 2x plus y plus z equals 3, intersecting a green line G. A projectile at P, 1, negative 2, negative 1, starts moving in the direction V equals 1, 2, 1. Which of the following is true? I'm just looking at the answers here. Okay. I think it's going to make sense if we first determine if it intersects the blue plane. And let's first write up the equation for the actual projectile. It should be fine here, so I'm going to call it R of t. It's kind of standard. It's going to be 1 plus t, 2t minus 2, and of course t minus 1. Okay, so that is our R of t here. And if you think about it, and I guess these are x, y, and z components, if you plug it into, like, say, this blue plane here, we're kind of bound to have a solution because it's a linear, linear system of equations. So it's gonna intersect the blue plane and the yellow plane, but just we need to figure out in what order it's gonna do that. And for that, we can just plug in our values into the planes and determine which its value of t is smaller or greater. So let's first do the blue plane. I'm gonna do 1 plus t. We're going to get 3y, so we're going to get 6t minus 6. So I'm just going to do it like this. It just makes it easier to group together our terms. And then we're going to get negative 2t. Negative 2 times negative 1 is 2. So add these together, we're going to get 1 minus 6, negative 5, plus 2, negative 3. Negative 3. 7 minus 2 is 5, plus 5t equals 6. 5t equals 9, therefore t equals 9 over 5. Pretty nice here. And then we can do the same thing for plane y. We're going to get 2 plus 2t. And I guess I should just do equals 3 here, just to make it a little bit more, sorry, not 3, 6. 3 is the yellow plane. Plus y is 2t minus 2. And z is t minus 1. I kind of messed up the order here, so y is negative 2 plus 2t. Z is plus t minus 1. Okay, very nice. These are going to cancel. We're ending up with 2 plus 2 is 4, plus 1 is 5. So 5t minus 1 equals 3. Therefore, t equals 4 over 5. Pretty simple here. Linear equation. So this t is smaller. That means it's going to intersect the yellow plane first. And I guess we should also check if it intersects the green line, but just looking at our answers, using the answers, that's not really possible here because it's going to intersect the yellow plane and the blue plane. So it looks like B is our only answer here. C doesn't consider the fact that it intersects both of those other planes, so that is not our answer. So B is our answer here. Number 5, find an equation of the tangent plane to the paraboloid z equals 1 minus 1 over 10, x squared plus 4y squared at the point 1, 1, 1 over 2. Okay, I was like rewriting this in f of x, y, z, so we can find the gradient or the normal vector much easier. So we're going to get x, y, z. I'm just going to subtract x from both sides. We're going to get 1 minus 1 over 10 x squared. I guess I could keep the parentheses, or we could just distribute minus 4y squared over 10, and then of course minus z here. I'll just make that z a little bit more z. Okay, yeah, not sure if that's better, but looks fine. Okay, and then of course grad f x y z is our directional vector, is going to be given by negative 2x over 10 is 1 over 5x. Negative 8y over 10 is negative 4y over 5, and negative 1 here. Okay, and we're just going to plug in 1, 1, 1 half. 1 half doesn't matter because our z is a constant anyways. So if we plug that in, we're going to get our, normal vector is going to be equal to 1 half, or 1 over 5, sorry, negative 4 over 5, and negative 1. And I just looked at our answers, and it looks like they're doing some tricks with us here. We don't even need to really compute it, because we know our x is going to be something with 1 over 5 in it, or a multiple of that, and our z is going to be something with 4 over 5 in it. And just looking at it, E cannot be true. Same thing with c, because the coefficients are the same, and we know that's not true. And looking at it again, it looks like b got it completely mixed up. The x, they put it as 4 over 5. So d looks like our answer here, because really what they did is, we have the equation of the plane, 0 equals whatever, f of x, or we really just have grad f x y z dot some point x y z. That's really what we have here. So they just added this stuff right here to the other side to make it all positive. So that's just how they converted it to positive 1/2 and positive 4 over 5. So yeah, that D is our answer. Number 6, what value of c makes the function f of x y is equal to x squared minus y squared over x minus y if x is not y, not equal to y, and it is equal to cx if x equals y. Okay, just thinking here. Okay, x minus y squared, or x squared minus y squared, we can rewrite that as x minus y, x plus y over x minus y, and very evidently these two cancel, and we're just ending up with x plus y. And what this is really asking is, if right now we have some sort of like discontinuity, it's not equal to, it's not kind of following the rule where if you go along the line x equals y or y equals x, something like this, we should end up at the same value. That's kind of what the thing is saying, for it to be continuous. So the limit really from both sides along the line y equals x should be equal to really just this thing right here. So if we consider that, if we take the limit along the line y equals x, or as, say, x goes to y, of this thing right here, x plus y, we want that to be equal to cx. So actually, I think I maxed this up. It doesn't really matter the notation, but we could just say y goes to x. Just, you'll see later. So evaluating this limit is pretty simple. We can just directly substitute x for y. So we're really just going to get 2x equals cx, and this is why I wanted to go x, y goes to x. I mean, x goes to y, y goes to x. It's really the same thing. But we have an x here. We could just have substituted that x for a y, and we've got the same answer here. So pretty evidently, the only c value that makes this true is c equals 2. So A is our answer here. Number 7, let f of x, y equals x squared e to the x plus y. Find a unit vector in the direction of most rapid decrease for f when x comma y equals 1 comma 1. Okay, we know really what we're just looking for is grad f x y over magnitude of f x y, and the magnitude is to make it a normal vector, and of course it says decrease, so we really need a negative sign in front. Don't forget that. That is very important, and you will get played by the test writers if you don't include that. So okay, let's get the grad f of x y. I think we're gonna have to use product rule, and yeah, we are. Gonna be 2x e to the x plus y. Or sorry, I said product rule and I didn't do it. X squared e to the x plus y, and of course x squared e to the x plus y. Let me just make that a little bit better here. My handwriting is suboptimal at the moment. Okay, and then now we need to plug in 1 comma 1 here. We're going to get grad f 1 comma 1 is equal to 2e squared plus just e squared comma e squared. And of course, we forgot the negative sign. Let me write that in very bold font here so we don't forget. And that is just really equal to negative 3e squared. I just brought in the negative, doesn't really matter here. E squared. Okay, and of course, we need to divide that by the magnitude. And the magnitude of that is really, let me just rewrite it. We're going to get negative 3e squared, negative e squared. Magnitude of that is really just going to be square root 9e to the 4th plus e to the 4th. And if we do some combining here, we're going to get negative 3, rewriting. We're going to get root 10. e to the fourth, and we can just take out the we can take the square root of e to the fourth as e squared and just take that out here, just because e is positive here. It doesn't really matter. And we can see here that the e's actually cancel, so that's very nice. And we're just really left with -3, -1, all over root 10. That looks like it is D here. All right, number 8, find the minimum value of f of xy equals x plus y, subject to the constraint x squared plus 2y squared equals 6. Okay, this is our common Lagrange multiplier problem where we have grad f xy equals some lambda. I can't draw the lambda. Well, we will do. Okay. Lambda times grad g xy. And our grad g here is just going to be, really, we're going to have just grad g, or not g, so just our g, g of xy can just be x squared plus 2y squared minus 6. That just makes it the easiest here, and that's what you can always do. And we can write two equations here, one for the x component, so we're going to have partial derivative of that with respect to x, and so 1 equals partial derivative of that with respect to x times lambda. So we're going to get 2 lambda x. This is, I just kind of did it in one step here. And then, of course, we're going to have 1 equals partial derivative of this with respect to y times lambda. So we're going to get 4 lambda y. Okay, it's looking nice here. And I think I always like solving for the variables x and y and z, whatever we have here. So makes it much easier. So we're going to get x equals 1 over 2 lambda. And, of course, y equals 1 over 4 lambda. Okay. And then since we have this equation right here, we can just plug that in and solve for lambda. And hopefully we can actually solve for it. It's sometimes hard, but in this case, I think it'll be manageable. So we're going to get 1 over 4 lambda squared plus 2 times 1 over 16 lambda squared equals 6. Let me just move this a little bit over to make it a little bit more tidy. Okay, and this is really just 1 over 4 lambda squared plus 1 over 8 lambda squared equals 6. And if we kind of do some fraction algebra here, we're going to get 3 over 8 lambda squared equals 6. And of course, we can multiply both sides by 8, and we're going to get 3 over lambda squared equals 48. We can divide both sides by 48 and get 3 over 48 equals, or 3 over 48 times lambda squared equals 8. So let me just write that out here. 3 equals 48 over lambda squared. And then I guess we can just switch these two. 1 over 16 equals, that's not a 6. Come on. Okay, equals lambda squared. Therefore, lambda equals plus or minus 1 over 4. And, okay, it's looking like we're looking for the minimum. So we probably want to take the minimum value, or this negative value of lambda, sorry. So, circle the negative sign here. And then we plug it into our x and y here, and then add them up because our function is x plus y. So, plug in negative 1 over 4, we're going to get x equals negative 1 over 1 over 4, sorry, 1 over 2 here, and that is just negative 2. And y equals 1 over negative 1 equals negative 1, so our answer is just negative 2 minus 1, or 3 here. Okay, very nice. Number 9, the integral in spherical coordinates 0 to pi over 2, pi over 4 to pi over 2, 0 to cosecant phi, rho squared sine phi d rho d phi d theta. When converted to Cartesian coordinates becomes what? Oh, cosecant. Very disgusting stuff, if you ask me, but we will do here. Okay. I think if we get the rho bound out of the question and sort that out, it'll be easiest. So we're really going rho equals 0 to rho. That's a 70, not a 2. Okay. Rho equals cosecant phi. And I don't like working in cosecants. I like working in sines and cosines. So I can just write 1 over sine of phi. And that'll make it just so much easier because we can multiply both sides by sine phi and really get rho sine phi equals 1. And that is very nice because, as we remember, rho sine phi is, if we consider, say, this our rho, or our phi here, this is our rho, this is our rho sine phi. And kind of, if we think about this in 3 dimensions, and I can actually draw the graph here, this is static 1 right here because clearly rho sine phi equals 1. So we're going to have something where we're spinning around the z, or I guess, yeah, we're spinning around the z-axis here. So this is going to be something like this, but we need to determine the bounds of phi to know what it's actually doing here. And phi looks like it's going from pi over 4 to pi over 2. So if we draw that in 3D, pi over 4 is something like this, and this is of course pi over 2. So we're really going like, this is our bound, and don't forget we're going around. And this, don't get mistaken, this is not a cone. I'm just trying to help everyone visualize it a little bit better here. Yeah, so really what we're doing is going from 0, z equals 0, and of course, I should have mentioned, theta goes from 0 to pi over 2, so that's just this thing right here. And I don't really know how to make it a little bit easier to visualize, but I tried my best. I think now if we work on the numbers, it'll be a little bit easier. So I guess if we consider the theta value in like the xy plane, it's going to be something like this. That's our xy plane. But really what we're doing, kind of my drawing actually is kind of lets you see it. We're going from 0 to this thing right here because our phi goes from pi over 4 to pi over 2. So that's 0 to, I believe it should just be z equals, let's make that a better z. Z equals square root x squared plus y squared, because pi over 4 is just like y equals x. Y equals x, the line y equals x, and if you plug in y equals x to this thing here to get the traces, you're going to get z equals plus or minus x, and that's pretty consistent with what we have. So this is our equation for what we're integrating over. So we're going 0 to this thing right here, and so that pretty much gets out C, D, and E right here. So it's either up to A or B, and it looks like we're going to be going B here because, like I said, theta goes from 0 to pi over 2. And sorry, let me not erase that. If we draw that out, we're really going over y equals square root 1 minus x squared, so we're really doing this. We're so doing this region right here, and that's kind of what I drew up here. So that is consistent. So B is our answer here. Number 10, the double integral negative 1 to 1, 0 to square root 1 minus x squared y squared times x squared plus y squared cubed dy dx. When converted to polar coordinates becomes what? Okay, I always like doing the sketch here for the bounds here. Y is 0 to the semicircle, and x goes from negative 1 to 1. So we're really capturing this entire region. So that means theta goes from 0 to pi. Write out theta. And rho, or r in this case, not rho, r, what the, okay, r 0 to 1, because this right here is radius 1. Nice. And now we need to sub in x equals, or y equals r sine theta, and x squared plus y squared equals r squared. And we should be on our jolly way here. So we're going to get r squared sine squared theta times r squared cubed, and of course we know, I'm just really writing the integrand here because that's really all we need. We already have the bounds. Dy dx in polar is r dr d theta, so we're going to just multiply by another r. Dr d theta, very nice. So if we kind of distribute our r's here, r squared cubed is r to the 6th times our r to the 7th times our r squared. Finally at r to the 9th here. That's not a 9. Okay, 9. And then sine squared theta dr d theta. Okay, that's looking pretty nice. So just looking at the integrands, c, d, and e are out. And it's either up to a and b here. Hopefully one is right. Yeah, looks like it's a because like we said, theta is 0 to pi, and r is 0 to 1. Nice. Number 11, let f x, y, z equals, 3x squared, yz minus 3y squared, x cubed z minus 3x, x cubed y plus 2z. And f is conservative, or we can assume that. So we know if f is conservative, we're going to have some sort of scalar, I like to call it a potential function, where that's going to be equal to, or really, the gradient of the potential is going to be equal to our f vector. And really, if we have our x, y, and z components of the f vector, we can integrate each of the components with respect to x, y, and z, and calculate the potential, and then plug in the top minus bottom. And that is just the fundamental theorem of line integrals. This only works when f is conservative. That is very important here. Or the curl is 0. That's the definition of conservativity. Okay, yeah, I said it. So really what this is saying is potential of x with respect to x is 3x squared yz minus 3y. So we can kind of do like a imaginary integral with respect to dx and get x cubed yz minus 3xy. And yeah, that is kind of what we have so far. Just making sure I didn't make a silly mistake here. Nope, that looks good. Okay, and with respect to y is equal to, of course, the y component, which is x cubed z minus 3x. And then we can do the same thing, integrate that with respect to y. We're going to get, I can write it out, we're going to get x cubed yz minus 3xy. And when these kind of are looking similar or identical, we know we're kind of on the right track. So that's always a good thing. Let me move these up a little bit just to permit myself some more space. Okay, we're going to get, finally, z is equal to x cubed y plus 2z, integral with respect to z, and that is equal to x cubed yz plus z squared. Nice. And then to find our cumulative potential, we're going to add together all the unique terms, only include them once. So we're going to get potential equals x cubed yz minus 3xy plus z squared. And like I said, we need to evaluate that at the top minus bottom. So we're going from 0, 0, 2 to 0, 3, 0. Let me make that more like a 3. Okay, looks pretty nice to me. This is actually very nice because our x's are always 0. That means these are all gone. And really, z, the top is 0, so we're doing really just plugging in negative z cubed when z is 3, so it's just negative 4 should be our answer here. They made it pretty simple there to evaluate it. Number 12, evaluate line integral of c, x squared y dx plus y squared dy, where c is the boundary of the region enclosed by y equals x squared and x equals y squared. Oriented counterclockwise. Okay, counterclockwise is pretty key because we can use Green's theorem here. If we kind of see this format, we know it's more than likely going to be Green's theorem, or Green's theorem would be easiest to do in this case. And we always like easy. So, like I said, always sketch the region. We're going okay, it's a little bit crude. Something like this. Let me make that better, just to make it a little bit easier to visualize. Okay, and then we have x equals y squared. Really, we can rewrite that as y equals root x, and that's really just something like this. Get rid of this here because we're not considering that really, because we're looking for the boundary of the region enclosed by those two, so the bounded area. So we know if we call this component p and this q, this whole thing is just going to be equal to integral over some region d. I'm going to call this region here d. Really, these meet at some value here. We can get that later, of d of q with respect to x, or partial derivative of q with respect to x minus partial derivative of p with respect to y, dA, all here. So we're just looking to integrate this. And we should probably find this point right here. Well, if we set both of them equal to each other, we're going to get, or sub in our x here, we're going to get y equals y equals, I don't know, I can't, y to the fourth, and here, we're just going to get y equals 1. I mean, I can kind of see it here anyways. So this is going to be 1. X equals 1. Y equals 1. I mean, if you just think about it, the parabola here and the thing, the square root function, they're really just going to intersect at 1. The square root of 1 is 1. 1 squared is 1. Okay. Establish that. So we're just looking for the bounded area. And we should probably compute this thing right here. Let's first get the bounds for the integral. Well, if we do dy, I think it'll be easiest. So first, y is our parabola, so y equals x squared. 2 root x, like I said before. And, of course, this is dy, and now dx is just 0 to 1, because we're going from x equals 0 to x equals 1. Very nice. And now we need to compute this thing right here. So derivative of this with respect to x is just 0, so it's very nice. So really just end up with negative, write the nice parentheses, dy dx. Now we're looking for this with respect to y. We're going to get nice x squared here. Okay, so now we just need to evaluate this. Shouldn't be too bad. We can take out the negative, integral 0 x squared. Okay, and we can do a quick top minus bottom thing here because nothing depends on y here. So it's really just going to be negative integral 0 to 1. Should be a 2. Just make that a little bit clear. Okay, minus x squared dx. And this is really I think the hardest part of the problem. Really just getting the integral here. Really it's just integral 0 to 1. X squared times root x is x to the 5 over 2. It's really not going to matter here, I think. But let's just make sure. X to the fourth dx, I just multiplied them out just to make it a little bit easier. Just making sure, yep, that looks pretty correct. And now integrating this is x, or really 7 halves. So 2 over 7, x to the 7 halves. I guess the exponent doesn't matter. That's what I meant to say. Minus 1, or x to the 5th, over 5. Make that 5 a little bit acceptable. Okay. And this would really just be 2 over 7 minus 1/5. Do some, I guess, fraction math here. And, okay, we should be ending up with 3 over 35, I believe. 3 over 35 equals that right here. Okay, I see what we did. We just dropped the negative sign. So we really just want the negative sign here. Negative, whoa, okay. We're erasing our work. Negative sign here. And this should be negative 3 over 35. Just making sure 10 minus 7, yep, okay. And that looks like it's B. I mean, all the answers are negative anyway, so we knew that it wasn't too bad. Okay. Number 13, compute the line integral 2x plus y ds, where c is the line segment from 0, 0 to 6, 8. Okay, we can parameterize this pretty easily. R of t equals 6t, 8t, where 0 is less than or equal to t is less than or equal to 1. And we can find our R prime of t because we need the magnitude of that to multiply is 6, 8. And the magnitude of that is a nice just square root 36 plus 48. 36 plus 64 is just 100, is just 10. Very nice. And that is just R prime of t. Okay. So that just makes it very easy, I think, because the scalar here, no any trig sub, whatever. And now we just have to plug in our parameterization. And don't forget to multiply by the 10. 0 to 1, because we're really just doing I guess we do f of r of t times magnitude r prime of vector of t dt. That's our ds right here. Okay, and 0 to 1, we're going to get 16t plus 8t is just a nice 20t, not 20t squared, okay, dt, and that is just 10 times 10t squared, integral of that from 0 to 1, and that is just nice 100, and that is D. Number 14, suppose that phi of xy, phi, I don't know, equals x squared y minus y squared x. It's a scalar function. Let f xy be the gradient field of x, phi of xy. Compute f of 1, comma 2. Okay, we know f is really just grad phi, and we can compute that quite easily. So we're going to get 2x y minus y squared, and of course x squared minus 2xy. Making sure I didn't make any silly and obvious mistakes. 2xy minus y. Okay, that looks great. Plug in 1, 2. We're going to get 4 minus 4, and we get 0 here. And 1 minus 2 times 1 times 2 is 4, so we're going to get minus 4. And I definitely made a mistake here. Nope, it is minus 3. We have 1 minus 2 times 2, which is minus 4, so we have this right here. And oops, and the magnitude is, of course, just the square root of 9 or 3. So C is our answer. Number 15, the surface parameterized by r of u v equals 5 cos u sine v, 5 sine u sine v, 5 cos v is a what? Plane, ellipse, sphere, cylinder, paraboloid. Okay. Think what kind of makes most sense here is you can kind of we've seen this kind of surface before, and it looks oddly familiar or similar to spherical coordinates, where remember x equals rho sine phi cos theta, y equals rho sine phi, that's not exactly a phi, sine theta, and just z equals rho cos phi. Okay, it's just a little bit, it's looking a little bit familiar and similar to that, where v, I guess, is just phi and theta is just u. Just looking at this, cos theta, sine theta, yeah, I mean, it's pretty much identical. So if you sub in this and this into these, you're really just going to get the same thing as this. And that really just means that we have a sphere. In the case that you didn't immediately recognize it, to be honest, I would probably just start plotting points, even that sounds pretty unproductive. Or I would start just considering the cross sections, even though it's quite difficult here. But also, you could just think of it like a plane. We've seen planes. This just does not look like a plane. Planes just don't involve cosine or sine. An ellipse. The reason it's not an ellipse is because we have constant coefficients here. Ellipses would not have that. And cylinder. We've seen cylinders. They don't really have sine or cosine, even though you could. They actually do, but they don't have a cosine in the z component. They usually have something like just like a t or a u here. And same thing with a paraboloid. We don't have a cosine in the z component. So if you, I guess, just think about it, cosines, sines, multiplying them together, usually going to involve some sort of sphere. Number 16, a normal vector to the surface r of uv equals sine u cos u sine v at uv equals pi over 2 pi over 2 is what? Okay, so we're really just looking for normal, that is r. So our normal vector to this is just going to be ru cross rv. Just making sure that's a v. These texts really look similar, huh? Okay, so we can get ru pretty easily. Just cos u. Very easy to mess these up, and hopefully I don't. Sine u, sine v, 0. Rv is given by 0. Cos u, cos v, cos v. Hopefully I don't make a mistake here. It's very easy. Okay, now we're looking for the cross product. If we just think about like I, j, and k, we're just looking for kind of the determinant like that. It's a little crude here, but you get the point. So cos, really, cross product is just the determinant. So let's do that. For the I component, we're going to get negative sine u sine v times cos v. Okay, cos v, sine u, or sorry, no, that is totally wrong. Negative cos v sine, negative cos v cos u. Can't write today. And for the k component, we're just cos squared u cos v. And okay, I think if we think about it in terms of like substitutions, we know that sine u, or sine pi over 3 is root 3 over 2. And equals sine u, just a quick substitution, and cos u, or really, it doesn't, okay, no, I am mistaken, it does matter. No, sorry, it really doesn't matter because, sorry, u equals v. So any like sine term that you see is going to be root 3 over 2. Any cos is going to be equal to 1/2. So let's get to work here and just get rid of that. We kind of established that. So we have a sine u, sine v. So we're going to have, in the first, negative 3 over 4, sorry, times a 1/2. Second component, we're going to have not a root 3, a 3 over 4. I can't write today, okay. And a cos squared u, so 1/2 times 1/2 times a 1/2. It's very nice here. So we're going to really get negative 3 over 8. 3 over 4 is just 6 over 8. I'm going to 6 over 8. And, of course, okay, no, I see what I did here. This is not supposed to be. This is a 1 over 4, not a 3 over 4. Just because we have a cos u, cos v. So 1 over 2 times 1 over 2 is 1 over 4, not 3 over 4. 2 over 8, negative, or 2 over 8. Yep, that is actually negative. I forgot to carry that negative through. And, of course, 1 over 8. And if we look at this, the answers, they look like they don't have the over 8 or whatever, and they look like it just multiplied by 8. And that is just our A answer here, because we just take these, and that is negative 3, negative 2, 1, or A. All right, number 17, let f of x, y, z equals x squared y, y squared z, x squared y, then curl f is of 3, 2, 1 is what? Okay, we basically know that the curl of f is given by the determinant I, j, k, del x, del y, or d, whatever you, d, z, of the components. Make that more like a z, not a, I don't know what that is. Okay, hopefully I wrote those out right, and then we would take the determinant of that. So I'm just going to write the angle notation. Del y of xy squared is 2xy minus y squared. Y squared minus 0, but we need the negative, so negative y squared, just because of the sign pattern. Del x of y squared z is 0, minus x squared, so we're just minus x squared here. And we just need to plug in our numbers, and hopefully we're golden here. So we're going to get 2 times 3 times 2 is 12 minus 4. Oh, okay. Negative 4. And of course, negative 9. That is just equal to 8, negative 4, negative 9. And that looks like it is D here. Hopefully we did that right. I think it's very easy to mess up. I think let's just check this right here, the middle component. Del x of xy squared is y squared minus del z of x squared y is 0, but of course a negative. Okay, it looks like we did that right here. So just checking it over once more. Yeah, okay, that looks like it is correct. Nice. Okay, let 18, let S be an open surface in R3 with boundary curve C, where C is a circle in the xy plane with radius 1 and is oriented counterclockwise. When viewed from above, evaluate integral of C f dot dr, where f x, y, z is such that curl f is given by 1/2, negative 3/2, 1 over 4. Okay, so it's our classic like Stokes Theorem problem. We know Stokes Theorem basically really just states pretty bluntly that integral f dot dr equals the surface integral of the surface S. We can pretty much choose a surface. as long as it has the same boundary curve as C, and it's a closed surface, in fact. But we can, or open, it doesn't really matter. But yeah, it just has to have this boundary curve, the same as C here. So it is going to be, I guess I'll write it out, curl of F dot some normal vector, unit normal vector, ds, where S is just some surface area element. So whenever I see these problems, I always just think, like, what is the easiest possible surface that has this boundary curve that I can do? Just always easy. Just pick easy ones that are not going to be like some complex, like, I don't know, whatever. Just make it simple. And to me, the simplest surface that has this boundary curve is literally just a disk that lies in the xy plane here. So if we just imagine this as a curve, we can just fill it in, and that's going to be our surface. So we can just call that our surface S here. And as we can imagine, S is really just a circle, and it's oriented counterclockwise. So we really need to find our normal vector because we already have our curl. It's very nice by the test writers. So we really want our normal vector, and right hand rule, get your right hand and you kind of curl your fingers in the direction of C, and your thumb, when you point it out, it points in the direction of the normal vector. So in this case, the normal vector is going to be just straight out, like, out of the page. It's not really a good drawing, but maybe if I do a quick right angle here, that kind of helps. Yeah, okay. This is going to be our normal unit vector. So it's going to be out of the page because it's counterclockwise. Yeah. And I suppose even if you chose the wrong direction, you would be, you'd probably still get the right answer, because in the answer choices, they don't look like there's any negations of each other. So they're not going to get you there, I suppose. So our normal vector is just going to be straight out of the page, or out of the screen I'm recording. And it's going to be orthogonal, perpendicular to that xy plane, or the plane of the page. So it's really just going to be 0, 0, 1, and I just chose 1 because it's supposed to be a unit vector, and that means magnitude 1. So now we have integral S. We really have curl S. We have that, which is 1/2 negative 3 over 2, 1 over 4, dot 0, 0, 1. Let me make that a little bit more angle. ds. And that's just integral surface 1 over 4 ds. And since we established the surface is really just that disk, we can find the surface area on quotes, or just the area of that disk, very easily, because it's radius equals 1, therefore area equals pi r squared, and therefore the area is just pi. That makes it pretty easy. So, I mean, we really just have 1/4 integral of s ds, and integral of s ds is really just the surface area of our circle, which is pi, like we have. So really, this is just pi over 4. And if we didn't have a constant here, it'd be a little bit more tricky. We need to parameterize our surface. But since it's a constant, and this is really just, we don't really have a calculator or any complex math, we're going to stick with our simple numbers and just use our a equals pi r squared. So our answer is A here. Number 19, for which of the following vector fields is double integral over the surface f dot n ds not equal to triple integral of the region E dv if S is the closed boundary of the unit cube? They just wrote out the definition of the unit cube here. So really, this is our nice old divergence theorem here. Or that states that integral sf dot n ds is equal to triple integral of the closed region E divergence of f dv. Sorry, not s. I think s is just more fun to write, so I like writing it. Okay, and basically, if we look at this thing right here, that's analogous to the divergence of f dv, but it looks like the divergence is really just 1, because we have that imaginary 1 everywhere where we have a d something or dv. So it's really integral of 1 dv. And that means that the divergence of f or not dv, should just be equal to 1. And so we're looking for which of the one it's not equal to 1, because it says not equal. So I guess let's just start chipping away at our answers, and brute force is always the way. Not always, but okay. So A, let's compute the divergence. It's going to be 1 plus 0 plus 0, so A is not our answer because divergence equals 1. B is 3 minus 1 is 1, so that is not our answer again. And C, X, so it's going to be 1 plus 0 plus 0. It is 1, so again, that's not our answer. D, 1/3 times 3. Okay, not our answer, so E is probably our answer here. Let's just check. So we're going to get y squared plus z squared plus x squared. And that is not necessarily 1. That is equal to just r squared, or rho squared more specifically. So, and not plus rho squared. Okay, we are deleting everything. And okay, so that is our answer here, because, okay, we're also on the unit cube, so that doesn't really make sense that we're having a sphere here. So E is our answer, and we checked out all our other answers. The divergence equaled 1, so yeah. Number 20, find the outward flux of the vector field F equals sine y xz 3z squared, or 3z, across the boundary of the space between the two spheres, radii 1 and 2, both centered at the origin. Okay, this is another divergence theorem problem. We know that double or surface integral over f dot n ds, that's really just our flux. And kind of, if we wrote above, but we shouldn't, I guess I'll write it again. This is just the triple integral of the region E, divergence of f dv, and this is only true if it is a closed region, and in this case we have two spheres, so yeah, they will be closed here. If we just do a quick little sketch, hopefully these sketches not too horrendous, but okay. So it's just one sphere enclosed inside of another, and we're looking for kind of this region right here, I guess. Yeah, this region right here. We're looking for the flux of that. That actually looks pretty cool, I'm not gonna lie. I like my drawing here. Okay, so we're looking for really this integral where E is that region in the, whatever I marked up there. So in between these things is our E. So divergence of f, we can get that divergence of f equals, not going to be a vector, it can be a scalar, 0 plus 0 plus 3. Oh, we're very lucky, it's just 3 here. Got very lucky there. So now we're really just integrating of the region E, 3 dv. So we can pull up the 3, so that is just integral E, or more specifically, we can pull out the constant, just get 3 dv. And this right here is really just saying what is the volume of the region between those two things, those two spheres. And we can do that quite easy. Oh, where's our E going? Oh, no, okay, right here. All right, so that is just really pretty simple, because we know V of a sphere is just 4/3 pi r cubed, so we can compute that pretty easily. We have 4/3 pi. We can just factor out the 4/3 pi, and we can do the outer one minus the inner one. So we're going to get 8 minus 1, because 2 cubed is 8, and 1 cubed is, of course, 1. And then don't forget, we have the constant of 3 outside. So we need to multiply by 3, and that just comes from here. And cancel out the 3's here. We really are left with 27 pi. Or not 27 pi. 28 pi. Yes, okay, because 7 times 4 pi is 28 pi, and that is C here. Yep.